Welcome to the fairy tale of algorithms. Once upon a time, there was a guy called Kruskal. He had perseverance in the face of obstacles. He never gave up. After graduating from college, he joined a railway company called MST Corporation. The business of MST Corporation was about laying rails to connect cities. The most important problem that the company wanted to solve was how to lay the shortest rails that connect all cities. The smaller the total length of the rails, the more money they would save. In this graph, each node represents a city. Each edge represents a road that can potentially carry a rail. His goal is to find a combination of edges such that it covers all cities and that the total length is a minimum. That is to say, they needed to select some paths and abandon some others. How could they wisely select paths such that the total length is the shortest? This idea actually has a name, called the minimum spanning tree, or MST. What is MST? It's a subgraph of a graph. There are two requirements. Firstly, it has to cover all nodes in the graph. In other words, it has to connect all nodes. Secondly, among all possible combinations that satisfy the first requirement, the sum of the edge weight is the smallest. For example, this is an MST because the total length 22 is the smallest. You'll never find any combination covering all nodes that is less than 22. Another way to explain it is, if you grab any node from the MST and lift the node up, all the nodes will be lifted up since they are all connected. And the stuff you are lifting up is the lightest. Let's talk about Kruskal. Like I mentioned earlier, Kruskal is a greedy guy. He decided to find the minimum spanning tree no matter how challenging it was. After thinking days and nights for 3 months, he finally found a beautiful solution. He presented it to the whole company, and everyone was excited about this breakthrough. Let me explain this idea to you. Kruskal's idea is simple. He scans all edges in a non-decreasing order and maintains a minimum spanning tree so far. Here, he starts from the shortest edge, DF. If the edge is safe, that means it doesn't create any cycles within the current MST. Then we add this edge into the current MST. Since we don't have anything in the MST now, this edge is safe and will be the first edge added to the MST. We keep collecting all safe edges until we get the complete MST. I'll let you observe how Kruskal solves the rest of the problem. Feel free to speed up and jump. Now he made it. Are you wondering about the correctness? Kruskal has proved that as long as we always check edges in a non-decreasing order, we will be able to get a complete MST in the end. You can ask him about the details. Now that you've got the idea, I want to introduce implementation of this idea further. The most important question is how to know if an edge is safe? How to know if adding an edge will lead to a disaster of cycle? For example, let's go back to here. When we are adding edge BC, how to know if the path from B to C doesn't exist in the current MST that we've maintained? Well, a straightforward way is to do a recursion. As long as there's a path that exists in the current MST entirely, that means adding the edge BC will create a cycle. Nice, we have a solution now. But isn't it a little bit slow? Try to think out of the box. Although our goal is to find a cycle, do we have to check edges? Can we check nodes? What if we could mark these connected nodes with a label? For example, we label these connect guys with a heart. Similarly, we label these guys with a star. We have two groups or sets now. Now to see if the green edge will form a cycle, we only need to compare labels of two nodes and see if they are the same. In this example, B and C are labeled differently, so they belong to different groups. Therefore, adding this edge will be safe. However, if we're adding this edge, we'll be in trouble. Since two nodes belong to the same group, there must be a cycle. So the edge is not safe to add. Nobody in this industry is more familiar with this task than Miss Union Find. Therefore, Kruskal invited her to check the cycle. Union Find has two powerful skills. The first skill is called union. She can merge or union two groups into one group. Another skill is called find. She can check if two elements are from the same group. Here's their workflow. Let's see how they collaborated. First of all, Union Find marks each node in different colors through the make set operation, because she knows that each node belongs to its own group initially. Then she scans all edges by non-decreasing weight. The first edge she scans is the F, whose weight is the smallest. She looks up the group that D belongs to and the group that F belongs to through the find set operation. Oh, they belong to the different groups. Therefore, edge DF is safe because there will be no cycle formed after adding it to the current MST. As a result, she adds edge DF confidently into the current MST and merges D and F into one group called D through the union operation. Kruskal repeats these operations on the rest of the edges. I'll let you observe how they solve the rest of the problem. Feel free to speed up and jump. Well done, Kruskal and Unifind. Kruskal enjoyed the collaboration with Unifind and appreciated her help very much. Miss Unifind was always ready to help others, so many people wanted to be friends with her. With the help of Unifind, Kruskal was able to solve the problem in OE log V time. Everyone in the company liked Kruskal, not only because he solved the problem for the company, but also because of his perseverance. People were touched by how much trouble he had overcome when checking every single edge in order to find safe edges. He had experienced much frustration, loneliness, and disappointment when knowing an edge was unsafe. However, he never gave up. He had his own pace, but no one could stop his progress. Although Kruskal was not the fastest, and even looked a little bit clumsy, who cares? He tried and he made it. His favorite saying was, "Life is like a box of chocolates. You never know what you're gonna get." There was another guy in MST Corporation called Prim. He was Kruskal's colleague. Prim was born very smart, and his IQ was about 150. He solved the MSE problem in 3 days. What's more, his solution is faster than Kruskal's. Let's take a look at this amazing idea. Prim always maintains a connected MST and grows it until all nodes are reached. First of all, he selected an arbitrary node as a starting point of this MST. As long as he hasn't reached all nodes, he'll never give up. When deciding which edge to select next, he always selects the shortest edge to the current MST. In other words, he always selects the edge UV such that one end U belongs to the current MST in pink, while the other end V belongs to the unreached nodes in black. In this way, he grows this MST more and more and finally gets a complete MST. Let's see how Prim works on the rest of this graph. Feel free to speed up and jump. Well done, Prim! Unlike Kruskal, the minimum spanning tree that Prim has maintained is always connected. The minimum spanning tree that Kruskal has maintained can be fragmented. Prim is always growing a single tree, but for Kruskal, it's more like completing a jigsaw puzzle, where you complete different sections first and connect them at the end. Now that you've got the main idea, let me introduce the implementation of Prim's solution. To find the shortest edge, we have to scan all the edges. Well, that is a little bit slow. So Prim invited Mr. Minheap to help. Mr. Minheap was a frugal guy. He only ate bananas as his meal. You give him a bunch of numbers, and he can always return you the smallest number in the fastest time possible. With the help of Mr. Minheap, Prim was confident in solving this problem quickly. In his solution, each node has a distance label, which is a v.key in the code. What does the key represent? It is the shortest distance from this node to the current MST. Let me walk you through the implementation. I can show you some examples later. At first, Prim marks the distance label of each node as infinity. Since there's no MST formed at this time, the distance from each node to this non-existing MST is infinitely large. Then, Prim arbitrarily selects a node as a starting point of the MST and sets the distance label to 0 because this node has no distance with the current MST so far. Basically, he can start from whatever node he likes because the final MST will include all nodes anyway. As long as he hasn't reached all nodes, he'll never give up. Next, Prim will need to find a node that is closest to the current MST. Since he's collaborating with frugal Mr. Main Heap, he gives all nodes to Mr. Main Heap and lets him extract the main. Of course, at this time, the smallest is the node we just arbitrarily selected. Let's call it node U. After that, Prim wants to add the edge who is responsible for this shortest distance. The first node doesn't have an edge like this though, so he skips. Here comes the most important thing, to update the distance label of all neighbors of U. Since he just included U in MST, all the neighbors V may now be closer to the MST. How does he update? He simply follows two steps. In step 1, he calculates the new distance of node V and compares it with the current distance label, v.key. If the new distance is shorter, that means node V is getting closer to MST after U was added, so the distance needs to be updated. Step 2. Update the distance and remember who the main edge is. Why I need to remember the main edge UV? Without edge UV, he will never be able to update the distance, so he needs to give this edge some credits by memorizing it. If the distance label never be updated in future, that means edge UV is the optimal and the winner. As long as he hasn't reached all nodes, he will need to repeat again. This time the main node is 5, that means the distance from this node to the MST so far is 5, thanks to edge 5. Since Prim memorized the edge 5, he added it into the MST. He got the first edge in this MST. Yeah! Next, update nodes who deserve. I'll let you watch how Prim solved the rest of the problem. Feel free to speed up and jump. You'll be amazed by how smart he is. done, guys! Prim appreciated Mr. Mayheap's support and gave him a banana tree as a gift. The important part of Prim's idea is the caching of the now shortest edge at each node. Therefore, he doesn't have to repeat the same calculation for a node every time he adds another node. Kruskal and Prim got promoted soon and became more and more famous within the company. Everyone else in the company appreciated their hard work, admired their abilities, and thought that they were very, very greedy. Don't get me wrong, in the world of the fairy tale of algorithms, greed is a good trait. It means that one can find the underlying tricks that save a lot of time in solving the problem. Not everyone can be greedy. In order to be greedy, you have to be bold but cautious. For example, Kruskal checks all edges in a non-decreasing order, not because he thinks it's easier, but because he mathematically proved that this will be fine. Similarly, Prim always incorporates the smallest edge into the MST because he proved that doing so would result in an MST. They look risky and aggressive since they found the underlying truth about this world.